Good morning, everybody. This is Randall Pike, and I'm going to be lecturing on eigenvalues and eigenvectors, continuation of the material we've started in the last lecture. So let's begin with the lecture notes here. So this time we're going to introduce two new concepts. One is the dominant eigenvalue of a matrix. This would be the largest eigenvalue. We'll also study briefly complex eigenvalues and complex eigenvectors in the context of 2x2 matrices. Okay, so let's begin again. Review a little bit of what we were talking about last time. Here's a 2x2 matrix, an arbitrary 2x2 matrix, and we compute its characteristic equation, and that is the determinant of lambda times the 2x2 identity minus this matrix A, which is, if we look at the matrix here, we get lambda minus A in the top left, a minus B, a minus B, a minus C, and then a lambda minus D. Okay, so we compute this quantity here. We'll get lambda minus A times lambda minus D minus BC. Okay, so let's work this out. So lambda squared minus, and then we see the terms that are proportional to lambda, A plus B lambda. And then we get the last term, which is an AD minus BC. Now, written this way, we recognize that the second term here is the trace of the matrix A, that is the sum of the diagonal entries, and the constant term is the determinant of this matrix A. Okay, so that comes out in the formula for a 2x2 matrix. So the term, so I'm missing a lambda here, so let me put that in here. Okay, there's a lambda here. It's a lambda squared. That's the lambda term plus determinant A. So the coefficient of the lambda term, lambda to the power 1, is the trace, and the constant term in the polynomial is the determinant. Now, let me just mention here that in general, there's a formula. We can extend this in general for n by n matrix A. We have that the characteristic polynomial, this is p lambda, remember, what we've been calling p lambda, can be written as lambda to the n minus the trace of the matrix A, so the sum of the diagonal entries, lambda to the n minus 1. And then you have the middle terms here, so some constants, which are not, no simple formula for them here, you'll have to compute them. And we work our way down until we get to the power 1 of lambda, and then the constant term turns out again to be the determinant of A. So we see once again the terms, the trace of the matrix and the determinant of the matrix appearing in its characteristic polynomial. Let me just remind everybody what trace of A is. The trace of A, so sum of diagonal entries. And then the determinant of A, that A, determinant of A. Okay, so that's two quantities that we can read off from the matrix itself that appear in the characteristic polynomial. Okay, so let's consider now what are the possible eigenvalues for this 2x2 matrix above. So to begin with, let's recall here, for reference, quadratic formula. Okay, quadratic formula for a quadratic. Okay, let me just clean that up. Okay, so this is for a quadratic polynomial. Let me just write one out, ax squared plus bx plus c. All right, so p of x equals that. And then the roots are given by the quadratic formula. So x equals minus b plus or minus square root b squared minus 4ac, over 2a. Now this quantity d under the root square root there, the b squared minus 4ac is the discriminant. The discriminant of this quadratic equation. All right. So let's keep this in mind when we study the characteristic polynomial of the 2 by 2 matrix. So we found above that p lambda is equal to a lambda squared. So it's this quadratic. So lambda squared plus a plus d, actually that's a minus a plus d, lambda plus ad minus bc. Okay. So the quadratic formula, let's apply it here to find the roots. Says that the roots lambda, let's call them, are given by a plus d plus or minus square root of, now we have a plus d squared minus 4a, which is 1, d minus bc. In the quadratic equation, the a was 1, but here it's 1 here, but not in our formula on the right. We called it a. So that's that over 2a. All right. So we see the discriminant here is this quantity, a plus d squared minus 4 ad minus bc. Okay. Now recall the various cases. If d is a positive quantity, strictly bigger than 0, then there's two real distinct roots. Okay, so two different distinct real roots. I should just say two different real roots. All right. When d is 0, there's one real root with multiplicity 2. So one real root with multiplicity 2. And I should write here algebraic in brackets, because that's what we introduced last term. That term algebraic multiplicity. This is what I mean here. And in fact, the lambda 1 and lambda 2 are just a plus d over d, a plus d over 2. All right, so there they are. Now, there's a third case when d is strictly less than 0. Now, in this case, I'll write it out. I'll write out what it is here, then I'll explain. So here we have two complex eigenvalues, two complex roots, I should say roots. I'm talking about roots, which will turn out to be the eigenvalues. Actually, maybe I should write that here, because this is what we're talking about, eigenvalues. Okay. Eigenvalues and eigenvalues here, okay, which are the roots of the characteristic polynomial. Okay, so when d is less than 0, there's two complex eigenvalues, and they are conjugates of each other. Conjugates of each other. Okay, and we can write them down now. So lambda 1 equals a plus d over 2 plus I square root of absolute value of d. And lambda 2, so, and I should put, I guess I should put 2 there. Yeah, sorry. And then lambda 2 will be a plus d over 2 minus I root absolute value of the discriminant over 2, where recall the discriminant I'm writing as, in this case it's negative, so I'm writing as minus 1 times this positive quantity, square root of d, so that when I take the square root of d, I'm taking the square root of minus 1 and the square root times the square root of the absolute value of d. Okay, hence I get this term I square root absolute value of D. Okay, so that's the possibilities here. We have two distinct eigenvalues. We have one real root with multiplicity 2, or we have two complex eigenvalues that are conjugates of each other. Okay, so this is the possibilities for 2 by 2 matrices. Let's look at some examples. Symmetric matrix. Okay, special case. So let me write this down. Emphasize a symmetric matrix. Okay, so this is the definition we call of a symmetric matrix. It's equal to its transpose. So it's a reflection across the diagonal. The terms are the reflection across the diagonal. So for 2 by 2 matrix that is symmetric, we'd have A, B, and D. So there's the diagonal entries A and D, but because it's symmetric, the B in the bottom, the term in the bottom left corner must be B also. Okay, so in this case, AT is equal to T. So that forces the two off diagonal entries to be the same. So in this case, when we compute the characteristic polynomial, we find that, let's see what happens. So I get lambda minus A, B, I should put a minus B here. I'm writing positive, so, okay. So I get lambda minus A squared. Sorry, not lambda minus A, that's a D there, right? Okay, so I'm going to get lambda minus A, lambda minus D, minus B squared, okay? Which, let's write it out as a quadratic so I can see what the coefficients are and we can analyze the eigenvalues. So it's lambda squared minus A plus D, as we know, the trace, minus the determinant of a symmetric 2 by 2 matrix, AD minus B squared, okay, AD minus B squared, which is now, sorry, lambda, yeah, so the discriminant, so what we want to study now is the discriminant. So the discriminant of this particular polynomial, D, is, so remember it's A plus D squared, sorry, minus, sorry, I'm looking at the wrong equation, that's just AD minus B squared, right? That's the polynomial, but the discriminant has, and actually that's a plus sign, isn't it? Good, AD plus AD minus B squared. So the discriminant is going to be B squared, which is the A plus D term, and let's not forget that lambda here. Okay, so there's my characteristic polynomial. So discriminant of this quadratic will be A plus D squared minus 4 times AD minus B squared. Okay, so what we're interested in is what is this discriminant, so we can see what are the possibilities of eigenvalues for the symmetric matrix in terms of whether we see real or complex eigenvalues. So let's rewrite this discriminant. Let's expand it out first of all. So it's A squared plus 2AD plus D squared minus 4AD plus 4B squared. Okay, so that is, so A squared minus 2AD plus D squared plus 4B squared. Okay, so yeah, plus 4D squared, which is A minus D. So I'm going to collect some squared terms. So A minus D squared gives me that first part, plus A minus D squared plus my 4B squared. Okay, so we see that the discriminant is actually a sum of quadratics, and it'll be strictly positive as long as A is not 0, say. So let's just take A not to be 0, or A not equal to D. Okay, so if greater than equal to 0, so we can make the case where it's strictly bigger than 0, though. So strictly bigger than 0 if, say, A is not equal to D, or B is not equal to 0. Okay, so usually it's strictly bigger than 0, and therefore symmetric matrix, we can say, well, it will be, actually, I should just make this correction. It's strictly bigger than 0 because both of these cases can't be true. If both of these cases were true, isn't that right? Yeah, AD. Okay. So symmetric matrix has real eigenvalues. Well, I should just say bigger than or equal to 0. So real eigenvalues, they could be the same though. So that's the case when the discriminant is 0. So symmetric matrix has real eigenvalues. So the complex case doesn't happen here. So this is what we're emphasizing here, no complex eigenvalues. Okay. So that's our result here. And I'll just add here that this is true for any symmetric matrix. Okay, so any size. Although we just did the calculation for the 2 by 2 case here, for any n by n symmetric matrix. And that's an important feature, as we'll see. The existence or non-existence of complex eigenvalues is often useful for us. Okay, so let's do some examples here. Let's start with A then. So I have lambda I. Well, I should try my different color here. So let's do lambda I minus A equals lambda minus 2, 4, 1, lambda plus 1. Good. So when we write out this determinant, minus 4, and simplify that. So let's first write it out. And this one I can I can factor this quadratic right here. So lambda minus 3, lambda plus 2. I see that my two eigenvalues are 3 and 2, and minus 2 here. Now in this case, let's introduce the term the dominant eigenvalue. So we say in this case, lambda 1 is the dominant eigenvalue. It's the largest one in absolute value, but it's the largest one because it's positive. So we just have to say that. So lambda 1 is the dominant eigenvalue. Okay, so that's the term right here, and it's lambda 1. Because lambda 1, and I'll just write it out in terms of our definition below, lambda 1 in absolute value is larger than lambda 2 in absolute value. So there's only two eigenvalues here. So that is the dominant eigenvalue. Let's go on to the next matrix, lambda I minus B, matrix B. So we compute its characteristic polynomial. So lambda minus 2, 3 minus 3, lambda minus 2. And we'll get lambda minus 2 squared plus 9, which we can expand to lambda squared minus 4 lambda plus 13. And we can compute, now that's a quadratic that's irreducible. So I can tell that its eigenvalues are going to be complex. So let's compute them. So minus b plus or minus square root of b squared. So 16 minus 4 times 13, 52 over 2, which is 2 plus or minus. Now this is 16 minus 52 is minus 36. Okay, so let's just put that in. Minus 36 over 2. So I simplify that second term. So that's going to be square root of 36 itself is 6. So 6 over 2 will be 3. And then I have the square root of minus 1, which is I. So there are the two eigenvalues. So lambda 1 is 2 plus 3i. And lambda 2 is 2 minus 3i. And once again, we see that they're conjugate pair. So lambda 2 is the conjugate of lambda 1 and vice versa. And this will always be true because of this property, because of this property here. Oops. Okay, I have to erase that somehow. Because of that plus and minus sign in the quadratic formula, that's giving us the conjugate pairs right there. Okay. Now, good. So that's the dominant eigenvalue. So just as a note here, there's no dominant eigenvalue. No dominant eigenvalue here. Okay, because there's no largest eigenvalue. No single largest eigenvalue. No dominant eigenvalue for B. So I've been introducing these terms. Okay. All right, so let's move on to a more complex case. We're going to write down the definition for the dominant eigenvalue down below. So complex eigenvalues and eigenvectors. Okay, so we've covered the topic of complex eigenvalues. Now let's talk about complex eigenvectors. What do we mean by that? Well, those are going to be the vectors associated to complex eigenvalues. And necessarily, they will also have complex numbers in their entries. So let's do it. Look at this example of this matrix B. So let's compute its characteristic polynomial. So we get lambda minus 3, 0, 0, 0. 6 minus 2, 0 across the first row, lambda minus 3, 0, 0, 5, lambda minus 1, 0, 2 in the bottom row, minus 5, and then lambda plus 1. So let's expand down the first column. So lambda minus 3 times the determinant of this 3 by 3 matrix, lambda minus 3, 5, 2, 0, lambda minus 1, minus 5, 0, 1, lambda plus 1, okay, which we can write out now. I'll expand across the first row now. So lambda minus 3, and then the 2 by 2 submatrix, the determinant of that is this one, 1 lambda plus 1. And so we get this polynomial, lambda minus 3 squared, lambda squared minus 1 coming from the diagonal product in that 2 by 2 matrix, and then plus 5, okay, which we'll write as lambda minus 3 squared, lambda squared plus 4. Okay, so this is already in factored form, and which is what we want because we want to identify the root. So lambda squared minus 4 is a irreducible quadratic. It has a discriminant that's negative, and those roots are easy to see to be lambda or plus or minus 2i. So lambda plus 2i will be 1. Minus 2i will be one root, and plus 2i will be the other root. So two complex roots. So we have, in this case, we have lambda 1. The real eigenvalue is 3. And I'll just note here again, multiplicity 2, algebraic multiplicity 2, because it appears as a double root in the polynomial. And then the remaining two eigenvalues are 2i and minus 2i. Remember, they always occur in conjugate pairs. So this one is conjugate of lambda 2. Okay, so here we have, we can list the four eigenvalues. Corresponding to the 4 roots of this characteristic polynomial right here, the 4 roots. I say 4 even though you see 3 distinct ones. It's because the first one, lambda 1 equals 3, it has multiplicity 2. So it's occurring twice as a root. And then lambda 2 and lambda 3, each one of those occurs once. So there's 4 eigenvalues there for this matrix. What we note here is that complex, we've seen it again above, but this is a general fact that the complex eigenvalues of a real matrix. So by real matrix, we mean a matrix that has real entries. Real entries. So the numbers are real. The entries are real numbers. Entries. The complex eigenvalues of a real matrix always occur in conjugate pairs. Okay, so that's a general fact for real matrices. So in general, a real matrix could have real and imaginary, real and complex eigenvalues. We've seen, and you've seen many cases where there's only real eigenvalues, but there could be complex eigenvalues. When there are complex eigenvalues, they will occur in pairs, okay, and in conjugate pairs, in fact. Okay, so you can't have, for example, odd number of complex eigenvalues for a real matrix. You cannot have that. It has to be an even number because they appear in pairs. So now we're going to go and identify the eigenvectors of a matrix that has a complex eigenvalue. So let's take this example. Let's compute its characteristic polynomial. So lambda minus 5, 6, minus 3, lambda plus 1. And we get, after a little bit of algebra, minus 4 lambda plus 13. And we apply the quadratic formula here, we'll see the two complex eigenvalues are 2 plus 3i. And if I know one, then I know the other because it's the conjugate, which will be 2 minus 3i. Okay. Now let's look at eigenvectors. Okay, so this is what we talked about last time. Once you've identified eigenvalues, you can go and compute the eigenvectors. So let's go through one by one. So for the first one, which is 2 plus 3i, to find the eigenvector associated with it, we study this homogeneous equation. So this matrix, lambda I minus a times unknown vector x, which in this case for this lambda is going to be 2 plus 3i times the identity matrix minus a, okay, x, which is this matrix here. So let's write it out. So 2 plus 3i, now minus a, so minus 5, okay, and then 6 is the next entry, and then minus 3, and then in the bottom right corner, I get 2 plus 3i plus 1. So that's my matrix acting on this vector x, and we're looking for zero solution or non-trivial solutions to that equation. Okay, so this is the system we study when we're looking for eigenvectors. So let's row reduce this. It's a homogeneous system, so I'll just work with the coefficient matrix. So row reduce. Okay, so now we need to use our complex algebra to do the row reduction. So let's just simplify that slightly. So it's let's do that simple algebra there. 2 plus 3i minus 5 gives me minus 3 plus 3i. Okay, and then minus 3 down there, 6 here. Now at 2 plus 3i plus 1 gives me 3 plus 3i. Okay, so notice when we have a complex eigenvalue, we're now looking at a matrix that has complex entries, which is not what we've been studying in this course, and it's not something we will study, but we're just using it here to be able to compute these complex eigenvectors, because those complex eigenvectors do have a role in the situation when you have complex eigenvalues. All right, so let's row reduce this. So I'm going to make my upper left corner a minus, a leading 1. Okay, so I'm going to divide by, I divided the top row by minus 3 plus 3i. So let me just remind you what the inverse of a complex number is. So recall on the side here, recall that the inverse of a complex number is the conjugate divided by the norm squared. Okay, so therefore this inverse, which I used here, so minus 3 plus 3i minus 1 is minus 3i over, now the norm squared here is 9 plus 9, it's 18. So we can simplify this a little bit to be minus 1 over 6, 1 plus I. Okay, so that is, that number minus 1 over 6 times 1 plus I is the number I multiplied the top row by. Okay, so that gave me the leading one in the top left corner. And you can see that the second entry in the top row is minus 1 minus I, because I multiply 6 by this number and I get minus 1 minus I. All right, and now I'm going to eliminate the minus 3 in the bottom left corner. So what I'm going to do is I'm going to add 3 times the new first row to the bottom row. All right, so that's my 0 there, and I'll get, so in my bottom row, initially it was 3 plus 3i, and I'm going to subtract 3 times the top row. So I'm going to add 3 times the top row, right? So plus minus 3 minus 3i, all right? So that's by creating this 0 here, okay? And that cancels out, so we get finally 1, 0, minus 1 minus I, 0. So there's my row reduced coefficient matrix. And now we read off the solution. So x1 is going to be 1 plus I times t, where x2 is the free parameter. So in vector form, I see this is t times 1 plus I over 1, and 1, okay? So this is my v1, my eigenvector. v1, and we can check this. We can check. Like I mentioned last time, it's good to check the computation. So a times v1, let's see what that is. So a was 5 minus 6, 3 minus 1, times this v1, 1 plus I, 1. Okay, so when we do that calculation, we get minus 1 plus 5i for the top entry, 2 plus 3i for the second entry. All right, remember we want to see, can we write this as a multiple of the vector we started with, which was 1 plus I and 1, and we see indeed it is, and that multiple it turns out to be 2 plus 3i, which is the eigenvalue, 2 plus 3i. So this is verification that it works. Okay, so let's do the next eigenvalue. So the next eigenvalue, so for lambda 2 equals 2 minus 3i, okay, we have the matrix minus 3 minus 3i, 6 minus 3, 3 minus 3i, once I plug that in. So there's my coefficient matrix of the homogeneous system, which I want to row reduce. And I row reduce this. So first of all, I divide the top row by by minus 3 minus 3i, which means the inverse of minus 3 minus 3i. Okay, and that gives me minus 1 plus I. Okay, so in this case, minus 3 minus 3i inverse is going to be minus 3 plus 3i over 18. Okay, so that's the using the formula above. So when I use that to multiply the top row, I'll get that, and then I'll add 3 times the top row to the second row, and I will eliminate the both terms in the bottom row. So in this case, I get x1 is equal to plus 1. Yeah, let's do that here. So it's 1 minus I t, and x2 equals t, my free parameter. So in vector form, this is x times t with the vector 1 minus I in the first component and 1 in the second. I'll call that v2. So that's the eigenvector. That's an eigenvector for the second eigenvalue. Okay, so once again, you can check this out, a times v2. Okay, so 5 minus 6, 3 minus 1, times 1 minus I, 1, and we'll get minus 1 minus 5i, 2 minus 3i, which we can write as 2 minus 3i times 1 minus I, 1. Okay, so it does work. And we also note here that the eigenvectors themselves are conjugates of each other, just as the eigenvalues are. Okay, their entries are conjugates of each other. Okay, so let's talk more about dominant eigenvalues. Um, so in many applications, the dominant eigenvalue uh, is useful. Okay, all right. So, for example, the discrete uh, linear dynamical systems we studied in the computer assignment. And then a page ranking algorithm that you see on the internet. Ranking algorithm uses the dominant eigenvalue somewhere in the calculation. Okay, so there's many more applications of the dominant eigenvalue, locating the dominant eigenvalue. So that's why this algorithm for computing it was created, and it's done by generating a sequence of vectors and vectors and numbers that are approximating the dominant eigenvalue and its dominant eigenvector. So that the dominant eigenvector is the eigenvector associated to the dominant eigenvalue. And as I mentioned above, the dominant eigenvalue, which in this case we're labeling as lambda 1. So these are the distinct eigenvalues of a matrix, square matrix. So it's an n by n matrix. So there doesn't have to be n of them, but there's k distinct eigenvalues. Lambda 1 is bigger than all the other ones, okay, for every distinct eigenvalue. So that's the definition of the dominant eigenvalue. So let's look at some examples here first to locate them. So for A, to find the dominant eigenvalue algebraically, you may think you just have to compute all the eigenvalues and then locate them. And this is what you could do. For certain matrices, like this diagonal matrix, we already know that the eigenvalues are the diagonal entry. So lambda 1 I'll call -3, lambda 2 will be 2, and lambda 3 will be 1. We see that this matrix has a dominant eigenvalue of -3, okay, because it's larger than all the, in absolute value, it's larger than the other one. So this is the dominant eigenvalue. Eigenvalue. And then for the next example, we can compute what it is. So it's also a diagonal matrix. So I can just write down what the eigenvalues are. Okay, so lambda 1 -3, lambda 2 is 3, lambda 3 is 1. But because these are the same, B has no dominant eigenvalue. No dominant eigenvalue. So generally speaking, there doesn't have to be a dominant eigenvalue for a matrix. All right, but in some applications, we look for the dominant eigenvalue. And if it has a dominant eigenvalue, this algorithm will allow us to find it. So here's the what we call the power method. So we have a symmetric matrix. Now notice symmetric means it's real eigenvalues. Okay, so I already know that from the beginning by this property of symmetric matrices. We're assuming it has a dominant eigenvalue. Okay, we're assuming that. So I'm not computing the characteristic polynomial of A and finding all its eigenvalues. In fact, this algorithm, this power method, is to bypass that and to find it in a different way, indirectly, because the matrices and applications can be extremely large. The page ranking matrix is millions and millions of entries, and it's practically impossible to compute the eigenvalues. But we can do this algorithm to locate it approximately. So the theorem says, okay, and you can read this in the book. So see page 357 in the text for discussion on about this and why it might work. we'll approximate this eigenvalue, dominant eigenvalue, dominant eigenvector. Okay, so what you do is you start off with a more or less a random vector in Rn. Okay, notice we're talking about normalized eigenvector. So unit, let me just remind you this terminology. Unit vector x means its norm is 1. Okay, all right, so we're starting with a unit vector. This is the x naught you see here. And we're performing this iteration. So the next vector, the x1, is obtained by multiplying x naught with a, that's here, and then dividing by its norm. So x1 is also norm 1. Okay, in fact, all these vectors you see here are norm 1 because they're normalized. On the right, you see that it's a vector divided by the norm of itself. Okay, but you see how we work iteratively. You start with a more or less random x naught. The only requirement we have is this one right here. I'll put it in blue. It's not orthogonal to the eigenspace. Okay, so we're assuming this matrix has a dominant eigenvalue, and associated to that eigenvalue is, of course, an eigenspace, which could be multidimensional. And we want we want this x naught not to be orthogonal to it. Okay, so in other words, I'll write it down here. X naught has a component in the eigenspace E sub lambda. All right, so this is the eigenspace E sub lambda, the eigenspace associated to the dominant eigenvalue. The fact that we want x naught not to be orthogonal to it means that it has a part component in E sub lambda. That is, we can write x naught as say y. Let me write it this way. Okay, as y1 plus y2. So here's two vectors. Okay, and y2 is in the eigenspace. Okay, so this is what we mean. Okay, so there's got to be a part of it in the eigenspace, and just to make it clear, we can say that this y2 is orthogonal. Okay, so I'm not writing x naught in a tricky way where y2 is in the eigenspace and then y1 just happens to be the negative of that y2. No, I'm writing it so that x naught does have a piece in the eigenspace and what's left over is not in the eigenspace. Okay, the y2. So we just have to make a selection like this, which may be tricky because we don't know what the dominant eigenvalue is, and therefore we don't know what the dominant or the eigenspace is. Okay, but it will come out in the iteration when you work it out. Going back to this sequence here, so you see you started with this initial more or less random vector, and you generate the x1 by multiplication, you generate the x2 by multiplication by a of the previous vector x1, and then normalizing it, and you work your way down. So you're creating these vectors x1, x2, xk, etc., etc. Now, this next sentence is telling us that this product, this is a dot product of ax with x. Okay, in the case x is x1, x is x2, x is xk. This will converge to the eigenvalue. Okay, so the sequence of vectors is converging to a dominant eigenvector. Notice it will be norm 1. Whereas this sequence of dot products will converge to the dominant eigenvalue. And this makes sense here because if we did have an eigenvector, just think about it, eigenvalue lambda, then if we form this product with this vector, so ax dot x, okay, you're going to get, so ax is lambda x times x, you're going to get lambda times norm of x squared, okay, but if x is norm 1, then you just get lambda. So this formula, this sequence converging to the eigenvalue makes sense, okay? Because if the x i's are converging to the eigenvector, then it seems that this quantity should converge to the eigenvalue, and in fact that's true. So by generating this sequence of vectors x0, x1, x2, xk, we obtain two things. One is we obtain a dominant eigenvector, unit eigenvector, and we also obtain the estimate of the dominant eigenvalue. So here's the algorithm which you will use in a computing assignment, the last computing assignment. Okay, so computing assignment 4, you will work this out for yourself. And as described above, you start off with an appropriate x naught. Okay, that's the only thing you need to do is you need to make it unit 1, okay? And then you proceed with that iteration. So the first eigenvector, the next, sorry, not eigenvector, but the next vector in the sequence, x1, will be a times x naught divided by the norm. And therefore, the first approximation to the dominant eigenvalue would be this quantity here, this scalar quantity. Then you move to the next approximation to the dominant eigenvector, which is a acting on the previous vector, the previous estimate of the eigenvector. So ax1 divided by ax1. So it's normalized. x2 is normalized. And then you compute this dot product and see how close you're getting. Okay. So that is the that's the way the process works. Okay. So here we find directly. So directly, we found that we did this, I believe, right? So, okay, let's do this. So let's write it out. So lambda I minus A, the determinant of that. So lambda minus 3 minus 2 minus 2 lambda minus 3 will be, when you write it out, lambda squared minus 6 lambda plus 5, which we can factor into lambda minus 5 and lambda minus 1. So we see that lambda 1 is 5 and lambda 2 is 1. So this matrix does have a dominant eigenvalue. And then further, we can determine a dominant eigenvector. So let's do that here. So when lambda 1 is 5, I'll get, so 5 lambda minus A. Okay, so I'm going to row reduce this matrix to find the eigenvector associated with that eigenvalue. All right, so let's do that. So this row reduces to this one, this matrix, and we find that x is equal to the solution set t times 1, 1. So we'll take the normalized dominant eigenvalue to be 1 over root 2, 1 over root 2. Okay, so we've done the work beforehand. We've located the dominant eigenvalue and the dominant unit dominant eigenvector. So now we start the process, the algorithm, the power method. And let's just see it work in this case where we know the answer already. So we're going to take x naught to be 1, 0. Okay, so there's a unit vector. And therefore, my next computation will be ax0, which is 3, 2. Okay, but my second vector in the sequence will be x1, which is this vector ax naught divided by its norm. All right, which you can compute to be 1 over root 13 times 3 over 2, 3, 2. So I can write this one as a 3 over root 13, 2 over root 13. Okay, so there's my normalized vector x1. Okay, so now to get x2, we compute ax1. Okay, so ax1 you can check is going to be square root of 13. And the second component is going to be 12 divided by square root of 13. Okay, so there's my ax1. Now to get my x2, it's ax1 divided by the norm of AX1. So I normalize this AX1 vector, and we get this. So the norm of AX1 is 1 over square root of 13 plus 144 over 13, okay, times the vector, so root 13. So that's now a normalized vector, but let's simplify it so we can see what its components are. All right, so we get, in the end, 13 over square root of 313. Second component is 12 over square root 313, which is approximately, all right, for reference down below, 7.7348. Okay. And the second component is approximately 0.6783. And now our estimate for the dominant eigenvalue for dominant eigenvalue, okay, we'll work through, there's a sequence of estimates. Okay, so the first estimate is lambda 1, which is ax2.x2. Okay, actually this is the second estimate above, so let's write it that way. Okay, so let's compute this. So what we get when we do ax2, you get 39 plus 24 divided by square root 313, and then 26 plus 36 divided by square root 313, dotted with 13 over square root 313, 12 over square root 313, which turns out to be 4.9936, okay? So notice here's our estimate. So this is the second vector that estimates the dominant eigenvector, and it's getting close to 1 over root 2. 1 over root 2 is 0.7 such and such, as we'll see below, so it's getting close. And also the estimate for the dominant eigenvalue is already getting quite close at the second iteration. Okay, so that's the work we need to do to apply the power method, all these matrix multiplications, all these normalizations, and then all these dot products to compute estimates of the eigenvalue. So it's built, it's perfect for writing an algorithm in MATLAB or any computer. And here's the output of such an algorithm. So first of all, you're computing the A times the various, A times the various vectors, x0, you start with x0, then you compute x1, you compute x2, compute x3, and to do that, you're multiplying these vectors by a, and then you're normalizing them. So ax naught here, and then the first vector x1 is the normalized vector, which is what we did above, okay? And then the next, to get the next vector x2, you have to multiply this x1 by a, and then normalize it. So here we are now. And that this is our next approximation to the dominant eigenvalue, and you continue. So you write a loop in MATLAB or some program to do this, and you quickly generate these sequence of vectors, x1, x2, x3, x4, x5, and you can see that they're converging the entry-wise to a certain number, which is getting close to 1 over the square root of 2, and 1 over the square root of 2, which is what we found above, which is the actual unit dominant eigenvector. And now the eigenvalues, the estimates for the eigenvalues, here they are, lambda superscript 1, superscript 2, superscript 3, etc., are these dot products of the A with the estimate of the eigenvectors. So you can see these numbers themselves are also getting very close to the dominant eigenvalue. So they're here, we've already reached the dominant eigenvalue to 5 decimal places. And here we're getting close to the dominant eigenvector. Okay, so that's the power method, which will work in, given the hypotheses are of the method are satisfied. So you need a, here's the theorem up here. You need, first of all, you need the matrix to be symmetric and have a dominant eigenvalue, positive dominant eigenvalue. So that's not something you know when you start, okay? And then you have to select your x naught to be an appropriate vector. It's random in some sense, but the only condition is it's not orthogonal to the eigenspace, which is something you don't know. But typically, it's hard to pick a vector that's orthogonal to the eigenspace. So more or less, your random choice will work. And you perform this iteration. Now, if you recall the Newton's method for finding roots in calculus, remember things can go awry if the initial condition wasn't chosen properly, or the graph itself has a certain shape. Then the sequence that you get generated with Newton's method doesn't converge, and you notice that very quickly. So same thing here. If you start with a situation that doesn't satisfy these hypotheses, and you go ahead and you compute these vectors and scalar quantities, if they're not converging, then it means you're not satisfying the hypothesis. So change something. Most likely, you'd first change the x naught and try to find that one that does generate a converging sequence of vectors and the converging and therefore converging sequence of eigenvalues, numbers converging to the eigenvalue. Otherwise, if that doesn't seem to work either, then maybe something's with your matrix A. Maybe it doesn't have a dominant eigenvalue. Maybe it's not positive. Maybe it's not symmetric. Okay, so that's what you have to check if it doesn't work properly. So that's the end of the lecture for this section here, which is our second lecture on eigenvectors and eigenvalues. So I will see you again